Do you know which technology allows me to send a stream of data from one device to multiple devices, but only send it once and have it received by these devices? In this example, I've got an Ubuntu laptop, I've got an Android phone, an iPhone, and I've got a Windows laptop. These 4 devices are receiving a stream of data from this laptop. This laptop is sending one stream of data into the network. The term used here is called multicasting. Multicasting is used in networking in many places. Routing protocols such as OSPF and EIGRP use multicasting. If you don't know what those are, don't worry about it. A more familiar example may be on trading floors, where traders want to receive the same data on multiple computers at exactly the same time. Information such as stock tickers can be sent via multicasting. It's also used very heavily in IP version 6. Broadcasting, which is different to multicasting, has been removed in IP version 6. IP version 6 relies on unicasts and multicasts. So what's the difference? A unicast is a one-to-one communication. This is typically what you're used to. As an example, when you open up a web browser and you go to, for instance, google.com, you're setting up a session from your computer to Google. That is a single communication from one device to another, typically using TCP. So HTTPS, as an example, uses TCP as a protocol. Here, we are not doing that. We are not sending one stream of data to the iPhone, one stream of data to the Windows laptop, third to the Android phone, and a fourth to the Linux laptop. It's one stream of data. This device actually doesn't even know who's receiving the multicast. It simply sends a stream of data into the network, and these devices receive it if they've subscribed to the multicast. That's different to broadcasting. With broadcasting, we send one stream of data and everyone receives it. So unicast is one-to-one, multicast is one-to-many, broadcast is one-to-all. On a local segment, if you send traffic to the broadcast address, everyone receives that traffic. But broadcasts are often blocked by routers. So you can't send a broadcast, in most cases, from one subnet or one network to another. Routers will block that. We have what are called local broadcasts as an example, where we only send broadcasts within a subnet or a link. They are blocked from going to another subnet or another link by a router. It's really important that you understand these basics. Difference between unicast, one-to-one, multicast, one-to-many, and broadcast, one-to-all. Broadcasts are blocked in most cases by routers, so you won't be able to send traffic from one network to another using a broadcast. It's normally contained to stop what was called Smurf attacks in the old days and various types of nefarious activities. Basically, we don't want traffic to go everywhere. But as an example, an ARP request or address resolution protocol request is used on the local segment to discover the MAC address of another device. But let's look at multicasting. So in this example, I'm using an application called VLC. VLC is fantastic. I did turn the audio off here, but notice what I've got here is an application. I can turn the volume up. I've just turned it down for all of these devices. So this is VLC running on the iPhone as well as the other devices. As an example here, I could stop the stream or I could re-enable it. I have subscribed to multicast address 239.123, port number 1234. So if I click on that, that multicast should start up again. And there you go. Notice it's starting in a similar place to all the other devices. These devices are synchronized. Notice what happens when I stop the application on the transmitting device. These devices will all stop, and they stop at exactly the same point. This is not a one-to-one communication. This is a one-to-many communication where these devices have subscribed to the multicast. So I'll show you how to set this up. On the transmitting device, in this case, the Windows laptop, I'll go to Media Stream. I'll click Add. I'm going to select my video, which in this case is fiber small. I'm going to click Stream, click Next, and I'm going to display the video locally, but I'm going to add, in this case, UDP. Multicasting uses UDP, or User Datagram Protocol, not TCP, or Transmission Control Protocol, because the transmitter doesn't even know who's receiving the traffic. It could be one device, it could be thousands of devices. It doesn't know that. It simply sends one stream of data into the network. I'll click Add here. And the IP address I'll use is 239.1.2.3. In the old days, we had what were called Class A, Class B, Class C addresses. They aren't really used these days because of CIDR address notation. But an example of a Class A address would be 10. A Class B address would be 172. A Class C address would be 192. You've probably on your network seen 192.168.1 dot something as the IP address on your home router. 172.16 something something is a Class B address. 10.x.x.x is an example of a Class A address. We have those ranges in Unicast, but in multicasting it's a Class D address, 224 to 239 in the first octet. As an example, OSPF, which is a routing protocol, uses 224.005 and 224.006. Those kind of multicasts are scoped to the local subnet. 239 is an address that you would typically want to use for your multicasting. 239 is known as administratively scoped address. There are various multicast address ranges, which I'll put on screen, but I wouldn't try and remember all of them unless you're studying, for instance, for a CCMP or CCIE exam. 239 in this example means that I could set it to whatever I wanted to. I can specify the port number 123, and what I'll do is click Next. I'm going to enable transcoding. The encapsulation that I'm going to use is MP4 or movie. Video codec I'm going to leave at the original value, and I'll do the same for the audio. I'll click Save, and then I'll click Next, and I'll say Stream all elementary elements and click Stream. What you should notice now is these devices start sending traffic. Notice they all kind of synchronized. It depends on the cache, depends on the network. In this case, I'm on a Wi-Fi network. Little TP-Link router, not necessarily the best way to send multicasts, but multicasting is being sent by that device. Depending on the cache that you configure, it's then received by these devices and then streamed to the local device. Okay, so now let's get a little bit more technical. I am going to open up Wireshark, which allows me to see what's actually happening on the network. I'll capture traffic on the Wi-Fi network. What you'll notice here is there's a lot of traffic going to 239.1.2.3 from 192.168.1.113. ipconfig shows us that that's the IP address of that Windows laptop. So that Windows laptop is sending multicast traffic into the network. So I'll stop the Wireshark capture. And what you'll notice is something interesting with regards to the MAC addresses. Source MAC address is my device. ipconfig/all will show us that. MAC address of this device ends in EA68. So that's the laptop sending traffic to this special address, 01005E. That is the vendor code for multicasting. Notice how Wireshark shows it as IPv4 MCAST. Just like you'll have a vendor code for instance, an Intel network card or a Cisco network card. This is the vendor code for multicasting. And notice the next half of the multicast address is 010203. And this is where it gets a little bit weird because the host portion of the MAC address is actually only derived from the last 23 bits of the IP version 4 address. That doesn't make any difference here because if we look at the second octet, 1 in decimal is 7 zeros followed by a 1. So the first bit is set to 0, and that remains the same. So the MAC address is 010203. But if this was 239.129 as the second octet, 2.3, the first bit in binary would be set to a 0. So the MAC address for 239.129 2.3 would actually be 010203. The same MAC address is what we're seeing here. And that's why in multicasting, it's important that you make sure that there's no overlap between your multicast streams because only the last 23 bits of the IP address are used to determine the MAC address, not the last 24 bits. 239 is ignored. Last 23 bits gives us that MAC address over there. We can see the type field is showing us that this is IP version 4. You can see the IP version 4 address here. So host sending traffic to the multicast address. You can see the source port is 64631. Destination port is 1234. That's what I configured on these clients. So as an example, on the Ubuntu computer, if I stop this and I go media and I select open network stream and specify UDP, the address that I am subscribing to is UDP:// at 239.123, port number 1234. And notice if I click play, it should start at the same place as the other devices. because one stream of data is being sent into the network, not multiple streams. Now, there's a lot of fragmented data here as the traffic needs to be put back together again on the receiving side, but notice you can see information about the video being transmitted into the network. The most important part that I wanted to point out here is the well-known multicast address, 01005E. That's the vendor code for multicast, followed by the host portion using the last 23 bits of the IP address. Now, I can go into a lot more detail if you're interested. I've had some comments on previous videos that multicasting is the same as broadcasting. No, it's not. The advantage of multicasting over broadcasting is devices only receive the traffic that they want to. In other words, the traffic is dropped at the network interface card or NIC. It's not dropped by the CPU. If your device receives a broadcast, that has to be received by the network interface card and sent to the CPU. In other words, there's an interruption. It needs to process the broadcast traffic to see if it's for the local device or not. If I had a device on this network and I was sending a broadcast, that device would receive it whether it wanted it or not. It disturbs the CPU. Now, obviously with computers today, things have got a lot better than in the past. But in the past, when we had a single CPU, that was a problem because the CPU kept getting interrupted by the broadcast and couldn't do other things. Here, the network interface card or NIC drops the traffic depending on whether an application such as VLC has told it to receive traffic going to this MAC address associated with the multicast. So that's one big advantage of multicasting over broadcasting. Routers also, as mentioned, drop broadcasts to stop, as I mentioned, the Smurf attack from years ago. So the idea is, in this case, a multicast would be transmitted through routers. They use a special routing protocol such as protocol independent multicast or PIM. There are different types of PIM, which I won't get to in today's discussion, but we have PIM dense mode, PIM sparse mode, PIM sparse dense mode. Various routing protocols can be used to determine where the multicast should go in the network. So routers can be configured to forward multicasts and to forward them efficiently. On a network switch, as an example, a layer 2 switch, which receives a broadcast, will flood that broadcast out of all ports except on the port in which it was received. If you've got VLANs, you can contain the broadcast, but let's assume all devices are on VLAN 1. The traffic received on one port is flooded out of all other ports. That happens all the time. With multicasting, if the device is not intelligent, it will do the same. So a multicast received on a single port will be flooded out of all other ports. But if the switch supports something called IGMP Snooping, it can snoop on what are called the IGMP messages, Internet Group Management Protocol messages. That's how a device tells its local router if it wants to receive the multicast. So the PC will tell the router that it wants to receive the multicast. The switch can listen in or snoop in on those messages and only send the multicast out of the ports that have clients that have subscribed or subscribers to the multicast. So if you have 24 ports on a switch and only port 1 and 2 have subscribers to a specific multicast on that switch, traffic will only be forwarded out of those two ports. It won't be forwarded out of other ports on the switch if IGMP snooping is enabled on the switch. If it was a broadcast, it would just be flooded out of all ports. So multicasting is much more efficient than broadcasting. Don't interrupt the CPU. We can use IGMP snooping to only forward the traffic out of certain ports on a switch. You can also configure your routers to run a routing protocol such as PIM to only forward the multicast through a certain part of the network and not try and flood it everywhere. So broadcast again would be blocked, but if it was a pure broadcast and it was just allowed, it would go all across the whole internet as an example, or all across your entire network. We obviously don't want to do that. We want to contain the traffic to only the devices that want the multicast. So by using what's called a multicast tree, we can decide, for instance, to only forward the traffic here, but not forward it there, based on the tree built by the routing protocols. I just wanted to introduce the concept of multicasting. Multicasting is one of those technologies that a lot of people seem to struggle with. The idea here is only devices that want the multicast to receive it, other devices don't. Think about it as follows. If you don't want to receive a certain magazine or email listing, you don't subscribe to that. If you want to receive a magazine or you want to receive an email, you would subscribe to that list. Or in this case, you subscribe to the multicast and you would receive the multicast. People who haven't subscribed don't receive the multicast. Now let's take this a step further. In this topology, I've got two Cisco routers and a Cisco switch. This Windows computer is the transmitter, and here I've got some receivers. But notice in this topology, the VLC server is connected to router 1. Router 1 is connected to router 2, and then we've got these clients connected to router 2. In this example, I've got 2 phones rather than just a PC as shown in the diagram. Router 1 is also connected to the internet. Notice these 2 phones, the Android phone as well as the iPhone 15, are connected via Ethernet to the network. I've turned off Wi-Fi. They are receiving the multicast frame from the VLC server. And I can prove that by simply unplugging this cable between the 2 routers. Notice the server is continuing to send a stream into the network. It doesn't know who's receiving the stream, continues to send it, but notice these 2 phones have stopped at the same point. If I plug that connection back again, what should happen, and it might take a while, is that these 2 phones should start receiving the traffic once again. Hopefully you can see that the lights are blinking a lot here as traffic is being sent between the devices. What I'll do is simply start the stream again. Notice now that the stream has started on these 2 phones. If I unplug the connection between the 2 routers, the stream has stopped. But this is being routed from one network to another across 2 routers to a switch. This switch is running IGMP Snooping, which means a PC, this PC in front of me, that's also connected to the same switch, won't receive the traffic because the multicast is only sent out of specific ports. So switch 1 in this topology, the only switch that I've got at the bottom here, if I use the command show IP, IGMP Snooping, IGMP or Internet Group Management Protocol allows a client to tell its local router that it wants to receive a multicast. It indicates the subscription to the router. So it subscribes to the multicast to tell the router that it wants to receive the multicast. A layer 2 switch by default will flood multicasts out of all ports. But if we only want to send traffic out of specific ports, we can enable IGMP Snooping, which is actually enabled by default on the Cisco switch. So if I use the command show IP IGMP Snooping, groups, what you can see here is this group 239.123 has a port list of gigabit 101, 103, 104. Those are the ports that my phones are connected to. The PC that I'm currently working on is connected to gigabit 102. It's not part of that port list, so it won't receive the traffic. And we can prove that by running Wireshark on the PC. So if I run Wireshark, you can see a whole bunch of traffic. But if I search for that IP address, 239.123, notice no traffic is received by the PC, even though it's connected to the same switch. Traffic is limited. This is different to a broadcast, which would be sent out of all ports on the switch within a VLAN. In this example, traffic is only sent out of ports where hosts have subscribed to the multicast. We can look at our multicast router. The router is on gigabit 101, so you can see this little cable here, hopefully. That's how the router is connected to the switch. We can see who the query is, so who's querying the segment to find out who wants multicast. That's once again router 2 here, which has IP address 10.12254. Now, to make the point, I'm going to make this smaller. Notice no multicasts are shown on or within Wireshark. If I type the command no IP IGMP Snooping and disable snooping on the switch, notice suddenly I get multicasts on my PC even though I haven't subscribed to the multicast. In this case, the multicast is being forwarded out of all ports. So notice snooping is disabled for VLAN 1. So if I look at groups, we don't see any groups at the moment. Multicasts are being flooded out of all the ports because I've disabled IGMP snooping. If I enable IGMP snooping again, what should happen, and this might take it a while, is it should stop forwarding traffic to the PC. And there you go. Notice I'm not receiving any multicasts now. If we look at our groups, you can see that it's learnt this multicast should be sent out of those ports and not port 2 where the PC is. So the PC doesn't receive the multicast. Big difference between a multicast and a broadcast. With IGMP snooping, traffic is only forwarded out of ports where there are subscribers, so clients. So as an example, if I turn off this multicast on the phone, notice I can subscribe to that multicast. In this example, I'm using RTP rather than UDP, and I'll show you in a moment how to set that up. But what should happen is that port is removed from the list, and you can see that. So 239.123 is only being sent out of these ports rather than that port because we disabled the multicast. If I open up the network stream on the phone, what we should see is traffic is now sent out of that port. So there's the multicast on the phone, and you can see the IGMP list includes that port now. So Internet Group Management Protocol, or IGMP, is used by a client to indicate to the network that it wants to receive a multicast. So the phone actually sends an IGMP join message to the local router, to the querer on the segment. This router then forwards the multicast to the switch when there are clients that want to receive it. The switch in this example is using IGMP snooping, so it listens in on that message or snoops in on the message between the client and the router, and then only forwards the multicast out of specific ports. If IGMP snooping is disabled, the switch will receive the multicast and just flood it out of all ports, as I demonstrated with my PC. When I disabled IGMP snooping, the PC received the multicast. Okay, but how is the topology built? This client has no idea who's receiving the multicast. Routers build a tree to forward the multicast through the network. So what I'll do here is telnet to router 1 and log in. Show IP route shows me the unicast routing table on the router. So as an example here, we're running a protocol OSPF, Open Shortest Path First. That is a unicast routing protocol. If we use the command show IP mroute, that shows us the multicast routing table. And what you'll notice here is a device with this IP address is sending a multicast to 239.123. That is this device. So if I open up a terminal and I type ipconfig, you can see that's the IP address of this device, and it's forwarding multicasts to, and I'll just redo this actually so that you can see the whole process. It's forwarding multicasts to that address. So if I open up VLC, notice the multicast has stopped now, or the stream has stopped on these two devices because the transmitter, in this case this device, has stopped sending. So I'll go media stream because I want to start a stream, and I'll add the file, which is fiber small in this example, and I'll click stream. That's the file that we're going to send into the network. I'm going to display it locally, but in this example, I'm going to use RTP to forward the traffic to 239.123. And the port number I'm using here is just the default of 5004. I'll click next. I'm going to leave transcoding enabled. I'll leave all of these at their default values. So I haven't changed any of that. Click next. I'm going to stream all elements, but this is really important. You need to add the TTL here of some value. By default, VLC is going to use a TTL of 1, which means it will not hop across routers. The multicast will be contained within the VLAN or within the segment here, and it will never get to the other part of the network. So I'm just going to set the TTL to some large amount, let's say 50, and then click stream. And notice multicast is now received by these two phones from the PC. If we open up Wireshark on the transmitter, so over here, I'll be able to see that traffic. You can see that 10.1.1.101 is sending a multicast to 239.123. You can see the protocol is UDP. Notice the MAC address is the PC sending a multicast to the multicast network address 01005E, followed by the MAC address of the multicast 0123 in this example. There's the source IP address, destination IP address 239.123. What I want to point out here is notice the TTL, time to deliver, set to 50 because I set that within the VLC application, which means it can hop across a whole bunch of routers. So I'll stop that. So multicast is going into the network. Now multicast has to build a tree to send the multicast from the transmitter to various clients in the network or receivers in the network. So the sender in this example is this device. Notice that IP address is sending a multicast to 239.123. In this example, the incoming interface is VLAN 1. On router 1, this PC is connected to this port, which is in VLAN 1. Notice there's a switch port in this router. Traffic is arriving on this port, which is in VLAN 1, and it's being transmitted out of gigabit 000. Notice the outgoing interface list is gigabit 000. So this transmitter just sends the multicast, doesn't know who's going to receive it. That's what's interesting about multicasting. The transmitter just sends it. It doesn't know who's going to receive it. The multicast from the transmitter hits the router. on VLAN 1. Outgoing interface list is gigabit 000. How did it learn that? Because I'm running PIM sparse dense mode. To enable multicasting on the router, in this example, it's Cisco router, I use the command IP multicast routing distributed. Unicast routing is enabled by default on a Cisco router, but multicast routing isn't enabled by default. So we need to enable that. And then we need to enable PIM or protocol independent multicast on our interfaces. In this example, we're running sparse dense mode, which is the recommended mode. In pure sparse mode, you need to configure a rendezvous point. In dense mode, it normally floods and then prunes the multicast. We'll cover that in a separate video if you're interested. The moral of the story is, notice on the gigabit 000 interface, we've enabled PIM. And if I scroll down and go all the way to VLAN 1, notice it's also enabled on that interface. Basically, when this router receives an IGMP join message from a client, it tells router 1 to send traffic to it using that protocol. So if I type show IP PIM neighbor, notice it has a neighbor here on gigabit 000. So router 1 sees router 2 as a neighbor. And I'll telnet to router 2, show IP PIM neighbor, it sees router 1 as a neighbor. So it's also building a tree for the multicast. So show IP mroute. This host, the PC at the top here, is sending a multicast to 239.123. Incoming interface from router 2's point of view is the gigabit interface. So router 1 forwards the traffic to router 2 using this gigabit interface. Router 2 is then sending it out of VLAN 1. VLAN 1 is configured on these ports. So this interface then forwards the traffic to the switch, which then sends it to the clients. And again, I can prove that by simply unplugging some cables. So as an example, if I unplug this cable here on the router, that interface goes down. I've lost my connection now because I was actually telnetting to the device. But what you'll see is the multicast has stopped on the clients. If I plug that in, what should happen is the multicast should be sent again. There you go. Multicast has started. I'll telnet back to that router, show IP mroute. Again, that sender is sending a multicast to 239.123 and incoming interface is gigabit 000. Outgoing interface is VLAN 1. Traffic from here through the blue cable to the router. Router sends it across this gray cable, comes here. This router is forwarding it across the gray cable to the switch, which then sends it to the ports that have subscribed to the multicast. Multicasting is a whole big topic. This, however, gives you a basic idea of multicasting. Again, on the routers, I have enabled multicasting globally. And then on the interfaces that I want to run multicasting on, I've enabled PIM sparse dense mode. So gigabit 000 and on VLAN 1, I've done the same. Multicasting relies on a multicast routing protocol as well as a unicast routing protocol. So I've got OSPF here for unicast and I've got PIM sparse dense mode for multicasting. It also requires IGMP. So show IP IGMP groups on the router. This is router 2 connected to the switch. We can see that multicast is going to be sent out of VLAN 1. The last reporter, in other words, the last device that wanted a multicast was 10.1.2.102. If I simply unplug these cables on these two phones, the stream will stop on the phones. And what will happen is notice that device is removed. The multicast is no longer going to be forwarded out of that interface. Show IP mroute. The tree gets pruned back. So on router 2, for this multicast, notice the outgoing list is null because no one is receiving the multicast, so it doesn't forward the multicast onto the network down here. In other words, the switch won't receive it. We are pruning back the traffic to conserve traffic on the network. On router 1, show IP mroute. What you'll also notice is for that multicast, it's been pruned. The tree has been pruned, so we're not going to forward traffic into the network down here because no one wants the traffic. Depending on the multicast protocol that you're using, we will build a tree and then prune it back if no one wants to receive the multicast, or it'll be pruned and then grow depending on clients that request the multicast. So what I'll do now is plug these clients back in. They should send IGMP join messages to router 2. and the tree should be built back. So notice it's still showing prune here on router 1. On router 2, outgoing interface list is still null. We've got to wait for something to happen. I've seen that sometimes it takes a while for the phones to send their messages. So what I'll do is start the application again and open up the stream. Hopefully that'll start now. There you go. Hopefully it'll start on the iPhone. I've sometimes had the iPhone take a while, but I mean, we have got a stream going at the moment. So, I mean, this is not a great idea with an iPhone to use a connector so big. I should use something small like this, but I haven't got enough here. So hopefully this will eventually connect. But having one client is good enough. So on router 2, notice we are forwarding now out of VLAN 1. And on router 1, we are forwarding out of gigabit 000. Notice forward previously on this router, it was pruned, but now the traffic is being forwarded because this router 2, informs router 1 that there are clients that want to receive the multicast and it should forward the traffic through the network. I could do something similar on my computer as an example. So in VLC, open network stream, specify the network that I want to connect to, so RTP and that address. And notice I'm also receiving the multicast on my PC now. So if I look at the switch, so on the switch, show IP IGMP Snooping, let's say groups, you can see the multicast is now forwarded out of gigabit 1, 0, 1, 2, and 3, not out of this interface because it looks like the iPhone is struggling to get that interface running. But there you go. I've now shown you weird network traffic. In this example, the sender or transmitter doesn't know who's receiving the traffic. It simply sends one stream into the network. The routers build a distribution tree to forward the multicast into the parts of the network where there are clients that have asked to subscribe to the multicast. If there are no clients who want to receive the multicast, the tree is pruned back to stop the flooding or forwarding of traffic into parts of the network that don't want to receive the traffic or don't need the traffic. We use IGMP snooping on a switch to only forward the multicast out of specific ports, much better than broadcast, which just flood the traffic out of all ports on a switch, such as a layer 2 switch. Hopefully you've learned about multicasting. Let me know in the comments what else you want to see. Do you want me to go into a lot more detail? I'm thinking of going deep into networking protocols, deep into networking. I did my CCIE many years ago, and the stuff that I've been teaching on my channel is just the tip of the iceberg of the stuff that I've learned and stuff that I've used in the past. If you're interested, let me know. I'll cover multicasting, I'll cover MPLS, BGP, routing protocols. I'm thinking of going really deep, but let me know what you think.